If you zone out, you can go back and watch them, but this is for the two girls who asked me to record it. 2.1, the derivative and the tangent line. So in order for us to have a good idea what a derivative is, I need to make sure you understand the difference between secant lines and tangent lines. So I want you to go on your notes, put a little dot there, head on over, put another dot there, and label this secant. This is called a secant line. Not nearly as valuable for us as a tangent line, but there it is. Finding the slope of a secant line is pretty easy because that's algebra 1. That's change in y over change in x, rise over run, all that good stuff. But we don't call our points x1, y1, and x2, y2 because we are always working with them being functions. So when I label this point over here, I want you to call it x comma the y at x, or f of x. And then the other point over there, we're going to call something else. What I've done to get to that point, go down here on the x-axis, I've scooted over this far. And I'm going to call this scoot a change along the x-axis. And we have two abbreviations for that. One of them's h. That's kind of universally a change along the x-axis. The other one is delta x, and it looks like this. It depends on what book you use. Okay, so our book uses both. Some books just use one. We'll use H primarily today, but that's just how far over you move along the x-axis to get from the left-hand point to the right-hand point. So when I go label this over here, I've obviously scooted over H. So if this was at 2 and I scooted over 5, I'd be at 7. I'm at x plus my change. Are you good with that? So my new point over here is x plus the change along the x-axis, and its new height is the f value, or the y at x plus the change. It's not nearly as complicated as it looks. Those are just 2 points. One of them was at x, f of x, the other one got moved over, and now it's at x plus h, f of x plus h. It's easy, right? You get that? So if I were to find the slope of that secant line, that'd be pretty straightforward. That's not our goal today, though. We're going to talk about tangent lines. Tangent lines nick a curve at only one spot. And those are our focus. This whole chapter is really on these tangent lines. You might say, I don't get why they're important. I'm going to talk about it. You don't need to write this in your notes. I just want you to watch. Had I been charting, let's say, this is in seconds and it's time, and I was charting something's distance in feet over here, right? When I find the slope of the secant line, I'd be getting change in feet, change in distance, right, in y-axis, over change in time. What is change in distance over change in time, really? It's got another word. What is it? Speed, and I heard velocity. Yeah. So when you're actually calculating the slope of this secant line, and this was seconds, and you were charting something's distance, you would be finding its average velocity, right? What happened, like when I drove to work today, I would say my average velocity was probably about, I don't know, 70 miles per hour. Was that what I was going the whole time? It wasn't, right? So there were times when I was stopped. There was times when I was probably going 80. On average, though, I was going 70. The slope of the secant line does just that. It gives you an average, which is great, but historically, they didn't want to know the average. They want to know what happens right now, right? So not what's the average, like how fast am I going? How fast is something falling? How fast is this water tower leaking? How fast is this oil tanker spilling in the ocean right now? That's a pretty important concept, right? Like, I don't want to, why are we laughing? Because my headset looks so silly? Is it messing up my hair? What? I know I look like a dweeb. I apologize. I can't help it. All right. Don't make fun of me. Now it's all recorded. All right, anyway. So back up here. So the slope of the tangent line is actually what's happening right here at a half a second in. What is going on at that instant? Huge calculus concept of instantaneous versus average. And Newton's kind of credited for coming up with the connection between not just these lines geometrically, but an average rate of change versus what's happening right now, or an instantaneous rate of change. And that's what we're going to be concerned about. But first of all, I just wanted to draw a couple tangent lines on here so you can see it. I want you to draw a tangent line, so I need you to nick the curve so that its slope is 0. that the line you draw has to have a slope of 0 and it has to nick the curve. How many options do you have of drawing your line? Give me, how many? 2. There's 2 possible ones. Where are they? Where are they, Benny? Yeah, he said max and min last hour. Somebody said at the ups and the downs. Very important concept as well, because let me talk about the tie-in. The derivatives are, calculus is applied math, and we apply it to reach an end a lot of times in a physics or engineering realm, but that right there is very important. Do you think people in the real world would like to know where their math models for things max out or minimize themselves? Totally. So like in economics, I want to know, when's it at a maximum growth rate, or even biology, or something where I want to know when this population is at a maximum. That has to happen when the function itself turns. The function can't turn without its derivative being what? Or its slope, I'm sorry, I introduced the word without even telling you yet. Slope being 0. So huge concept. It seems silly, but the fact that this can only happen, the slope of the tangent line can only be 0 at these 2 spots is huge, because those are the spots that make the most and the least out of my function. Super important. Also, I said to draw one with a slope of 3. Notice if you're going to have a slope of 3, you can either be on this part of the graph or on this part of the graph. But what must the function be doing? Going uphill. Right? If I'm going to draw a tangent line, and 3 is pretty steep, so I'm going to go at where it's kind of going uphill. Tangent lines also tell us whether functions are increasing or decreasing. That's very important. Okay. Then it said, did it say -1/2 for the next one? Yeah, so -1/2, I am obviously going to have to be on which portion of that function to have my slope be negative? The decreasing part. Intuitively, you have just said about 5 really important calculus concepts. Really important. The fact of at 0 is, you even use the word max and mins, Ben. Somebody just said the function has to be going uphill. Then you just said it has to be decreasing. These are really important concepts that in order for me to draw that and have it be negative, the function's got to be going downhill. I put it more towards the top because -1/2 is a gradual decline, right? It's not a steep one. Anyway, on the next page here, I'll start to pick up the pace if I can. We have what's called the tangent line problem. I think I went 2 pages, which has this same graph, and we're going to label it the same way. So there's my secant line. I already said that that's x, f of x, so I'll write that a little faster this time. And then I scooted over h, and I got a new point. And Algebra 1 from the 7th or 8th grade for you guys, you know how to find the slope of that line. The slope of the secant's easy, right? How do you get the slope of any line? Through 2 points. Rise over run. What formula were you given for that? y2 minus y1 over x2 minus x1. That's what I'm going to do right now. We are going to take the second y. So I want you to write slope of secant, or let's even just write slope, and then let's put a little subscript here. Slope of the secant line is equal to, we'll do exactly what Kaya said. We'll do rise over run, which would translate into the second y minus the first y. This is really y2 minus y1 in function notation. Right, Joey? And then on the bottom, I would have x minus x. Well, what do I get when I do my x plus h minus x? H, yeah, it's that change along the x-axis. It's just an h. That should look really familiar to you. What does that look like? That was that circuit, right? We did a whole bunch of those. It was called a difference quotient. Really what you were finding when you were doing that difference quotient is really just a slope, a function for the slope, because your answer was like 3x minus 1, or so. It was a function, right? That's the slope of the secant line. Not particularly interested in that today. I want to get the slope of the tangent line, so go draw it. Well, you've always been told how many points do you need to get a slope? 2. Yes and no. Until calculus, you need 2. But we can do it with 1, because here's what we are going to do. So historically, again, I told you this represents an average rate that something's changing, and usually your x-axis in the real world is time. The y is whatever's dependent upon time. But if you were ever to do these in a real world context, time is going to be along the bottom axis, right? And then stuff will be changing over time. Maybe, again, like I said, maybe something's leaking, growing, I don't know. But finding the slope of that is easy. I just did it. Finding the slope of this, how am I going to do that? Well, let's go here. What if I drew my secant line like that? That'd be better, right? Wouldn't the slope of the secant now be a little bit better than what it was? How could I get it to be even better? I want my secant line to have the same slope as my tangent line. So what am I going to do with it? Make it closer. Yeah, and to make it parallel, because it's got to be a secant line, and there, that's a little better, right? How could I make it even better? I want it even to be better. Get a little closer, right? Now I'm getting a little closer, and I can still find the slope of these lines. I've got 2 points. It's getting a little better. What is h approaching as I'm getting that thing closer and closer and closer and closer and closer? 0. This is a limit, okay? This is a limit where I'm going to take this h, or this delta x, and I'm going to push it towards 0 so that I've barely moved at all. And as I do that, my secant line becomes the tangent line. So if I do slope of the tangent line, so I'm going to write slope subtangent. It's not really what it is this guy. That red line up there, as I squeeze it closer and closer and closer and closer, which means I have h approach 0. Keep in mind, h can't be 0, because if it were, I'd have 0 over 0, and that's our illegal guy. But this is really how I get the slope of that tangent line. Super important, it's the definition of a derivative. A derivative is, I would hope that if I asked everybody on your way out of the room today, which I probably will, if I said, what is a derivative? I would love it if you would say it's the slope of a tangent line. So what's a derivative? Slope of a tangent line. That's really what it is, okay? We have what are called numerical derivatives, and we have what are called functional derivatives. So when it's a function, it gives us the slope anywhere along a curve. If it's numerical, it does it at a specific spot. So we're going to work with finding those derivatives. We need notation for it, though, as well. So on your next page, I'll talk about the notation on the next page. So this is just it, big and bold in your face. So anytime from here on out, maybe some of you juniors, it'll be a long time. But every time we talk about a derivative, you're thinking several things. But one of them is a slope of a tangent line, and actually more application-based. It's an instantaneous rate of change. It's what's happening right now, not averaged out over the course of time. So there's notations, just like when I say find m, Sophie knows immediately when I say in math to find m, I'm telling her to find a what? Slope, right? Because that's just universal notation. Well, I don't want to have to say to Kevin, find the derivative of the function g, right? I want notation for that. So he reads the notation and he knows exactly what's being asked to find. There's several notations for it. If the function's called f, a lot of times we call the derivative f prime. And that's how we read that, f prime of x, which means the derivative of f. Sometimes, though, instead of f of x, we have y equals, and so we'll call the derivative y prime. So if I said that y is the function sine x, and I say, what's y prime? I'm asking you for the derivative. And what would I be asking you for? If this is the sine wave, y prime would give you the slopes of the tangent lines anywhere along it. Okay, so the other notation, more formal, and the one we're going to kind of try to use the most is dy dx. Put that in a box. That's formal notation. It makes sense, though. Some of you, when you were maybe taught slope, I know Kaya said rise over run, and then somebody said y2 minus y1. Did any of your teachers call it delta y over delta x when you were taught slope? Does that sound familiar? Well, that's what this is. This delta means change in. The only difference between the delta and the d, there's a minor difference between the two. The d means infinitesimally small, so it means like super small change, so close to 0. But dy dx means find the derivative of your function y. The other one that I haven't seen for a long time is a big D with a little x there, but that was actually, I used that when I was in one of my calculus classes. All that stuff means, hey, find the derivative. And the question for our whole chapter is, how do we find it? And in this section only, we're going to do it using what we call the limit process. It's kind of a pain, lots of algebra. You're actually going to take and force the secant line to come and match up and be the tangent line algebraically. But then we're going to have shortcuts. So that says limit process or using the definition of the derivative. How many days did it say we're going to use this process? 1. Okay, today. And then your homework for today, I want you to use the limit process, not the shorter rules. And it's not me giving you shortcuts. They're actually called derivative rules. But I'm going to give you the shortcut right now. When you're doing a polynomial function, which, you know, is like your x to the n's minus plus x to the n minus 1, all that kind of good stuff, the shortcut says you can bring the power out front, it's called the power rule, and drop the degree by 1. That'd be 2x. Okay, so I'm going to tell you when we do this the long way, my derivative will equal 2x. It will. I'm just giving you the shortcut because it always gets out there anyway. Like you have a brother, Vito, who is going to look at your entire assignment and do it in about 30 seconds because he's just going to go 4x squared plus 1x plus blah, blah, blah. It just is what it is. It happens every year. So I'm just going to blow that fun out for you and tell you the shortcut and still tell you for one day you have to do it the long way. All right. So I know that's what I'm going to get. By the way, when I tell you the derivative is 2x, what am I telling you? What does derivative mean? The what? Slope of the tangent lines can be found by doubling the x value. So what I'm saying is graphically, here's a parabola. That's the function y, or f of x, right here at 3, 9. The slope of this tangent line is 6. How'd I get 6? How'd I get 6? Yeah, and it gives me its slope anywhere. Now take a back to the concept that Ben said about maxes and mins. This has one minimum value. Where is it? At 0, right? The slope of the tangent line is 0. I can see it. Well, what does my derivative function spit out when I do f prime of 0? 0. It's telling me that's where the slope of the tangent lines is 0. All right, but we want to do it using the limit process. So what I'm going to be doing is taking any point on there and making a secant. Don't draw this on your notes. I'm going to take this secant line and I'm going to get it closer and closer and closer so it becomes the tangent line. Here's how I do that. I say it's a limit as h approaches 0 of y2, now known as f of x plus h, minus y1, now known as f of x, all over their difference, which is just h. And this is now what you did on Friday, evaluating a difference quotient. The only thing different is now we're actually going to evaluate the limit of it. Otherwise, this could have been on Friday's homework, so that should go smoothly. F of x plus h will square x plus h. You should know that by heart if you did Friday's homework. It was on there several times. Can somebody expand that for me without actually foiling it? What's x plus h quantity squared? X squared plus 2xh plus h squared. So I will be taking a limit. By the way, limits you always plug the number in, but if I put in a 0 here for h, I'm going to get f of x minus f of x, which is 0, over 0. That's an issue. So now I'm tackling the issue. How am I doing that? I'm going to expand that out. You guys said it's x squared plus 2xh plus h squared. That's f of x plus h minus f of x. What's f of x? X squared all over h. What happens at this juncture will happen every time. Anything without an h in it will cancel. If it doesn't, you did it wrong. I'll repeat that. Anything without an h in it will cancel. If it doesn't, you did it wrong. At this point, the same thing will happen every time. So it's a pain, a lot of algebra, but it's algorithmic, which means you do the same thing every time. At this juncture, when everything cancels off, what can I do to the top? What did you do for your difference quotient circuit? You factor the h out. Still going to do that. Here's the difference. I'm now taking a limit. So when I'm done, I'll have a little bit more cleanup. But an h comes out. I get 2x plus h. That'll always happen, by the way, because your goal is to cancel off the issue The issue is h in the denominator being 0. It's got to go. It can't go unless it factors out of the top. It can't factor out of the top unless everything else disappears. It's kind of cool how math works like that, right? So this is going to go. And just like we did in our limits chapter, now that I've canceled off the issue, I replug that in, and you'll notice I get 2x. What is 2x in this scenario? 2x is the derivative, which is the slopes of the tangent lines. I can write that 3 ways. I can write it as f prime of x. I can write it as y prime of x. I can write it as dy dx. Sometimes you'll even see it as d, and then it'll have the y in here, dx. All of this is saying the derivative is twice x. What does it do for me? It gives me the slopes anywhere. Why do I want to know the slopes? Because that's how things are changing. So it basically tells me how that function is changing. And usually when we start applying these in chapter 3, it's going to be something actually changing over time, like an actual scenario. And it becomes really cool to see how you can apply it. For now, though, you're going to do it the long way. It's going to be kind of a pain, but you'll deal. I think I'll talk about this later. All right? I think I'm going to skip this whole page for now. I'm going to go right down to, I think it's ahead of its time, so I'm just going to let that sit. I'm going to go down to the bottom and have you take out your calculator, because your calculator will do derivatives. I need to tell you where it does them and then talk about what kind of a calculator you have, because some of yours are going to look a little different. Anyone have the TI-83? Good. Not a fan. That one I can't upgrade. If you have a TI-84 that's not a silver edition, it's going to look different, but I can link to somebody else's and I can give you a new operating system really easily. So you'll know if you have the right kind of calculator in just a second. So there's 2 ways actually you can do derivatives and integrals, but after teaching this for 6 years now, we never end up using the second way. So no sense teaching you 2 ways when we're going to go to 1 only. And that's going to be to use Math 8. So I want you to hit your Math 8 option. Those of you with the Inspire, you will have a calculus catalog somewhere that it'll say derivative. Like you have a calculus menu. We don't have a calculus menu on the 84s. We just have the math. But if you go to math and you go to number 8, it should pop up this little notation. It'll say D box, and then there'll be parentheses, and then it'll say x equals, and then another box. Whose says n deriv? I can fix. Okay, so you can still do it on that one. It's just a pain to enter. We can just connect you to somebody else's and give you a new calculator. All right, anyone else? Just one I need to update. That's great. Usually I have like 5 or 6. I think it's because the math department's starting to request that you buy the TI-84 silver editions, which is great. Yes? Yeah. It depends on the calculator. So here's how you tell it. You put an x in that one. It's a derivative with respect to x, which for us that'll always be there. Then you put the function that we're working with. It's x squared. And then I already told you we did this one by hand. We said the derivative was twice x, right? So at 4, my derivative better be 8, right? Your calculator will tell you that. Just enter a 4 and enter equals, and your calculator will tell you the numerical derivative. It can't tell you that the derivative is twice x. It can only do it at a specific point. All right, did you get your calculator to go? Yours, you have to enter the function, comma, x, comma, the number. Yeah, you'd have to, I think it says n deriv and it's sitting there. You have to go x squared, comma, either the number and then x, or these might be flipped around. And that's the problem with the 83. It's not intuitive what to do. The 84s, it's pretty clear, fill in the boxes. So how many of you got an 8 to pop out? Do it one more time. Do the derivative of x squared at 0. That's where the min was, right? So what should your calculator say? 0. Slope of the tangent line should be 0. Your calculator will tell you that. Pretty valuable when we're calculator active. And on some of the real world application problems on the AP exam, the functions are pretty beefed up. So if it's calculator active, you can just do its derivative right there. All right. Today, not focusing on that a whole lot. So we'll go do another one by hand. Now, according to what I told you, for the shortcut, it's not even a shortcut, it's called the power rule. I am allowed to bring the power out front, drop the exponent down 1. Did you notice how my parabolas, x squared became 2x a line? That's always the case, by the way. A derivative is always 1 degree less than the original. So cubics go to quadratics. More on that later when we get to graphing. So I've got this cubic function. Its derivative, I'm going to call it dy dx this time just to kind of get the notation going for you. Shortcut, bring the 3 out front. Knock the degree down 1. Next term, bring the degree out front, which would be a 1 times 2. Knock the degree down 1 to 0. What's anything to the 0 power? 1. And my constant. Why? She memorized it. Great, because she's had this before, but it is. The derivatives of constants are 0. You'll always know that. It becomes easy, but here's the why of it. A constant function like y equals 3, what kind of a line is it? Y equals 3, what is it? Horizontal line. What's the slope everywhere? 0. So constant functions always have derivatives that go to 0. So this is my answer. Now getting that's going to be quite the amount of work getting it by hand. So you'll see that's why for one day we do it by hand. Honestly, its biggest bonus is the algebra that's required. It gets your algebra up to snuff. How do we do it by hand? We take a limit as h approaches 0. Basically what we're doing verbally is we're squeezing the tangent line and the secant line on top of each other. We're forcing them to line up. They can't quite get there, but I can get to point 1 before I croak and die, right? And I'm still not, it's so close that it might as well be equal. So we do f of x plus h. Well, I need to figure out what x plus h is. You have 2 options. Maybe you remember from your circuit how to expand x plus h cubed. If that fails, you do it times itself with a little foiling, and then you do some distributive property, right, Eli? And then you clean it up, but I'm confident you could do it, so I'm not going to waste your homework time. You would have to do x plus h times x plus h times x plus h. Does anyone in here just remember what it was? Because it was on your circuit twice. You got it, Sophie? Mm-hmm. Yes. There it is. X cubed plus 3x squared h plus 3xh squared plus h cubed. That's this. Then I have to do plus 2 times it. Then I have the minus 3. FYI, all I have just done is f of x plus h. I was supposed to take the input, cube it, plus twice the input, and subtract 3. That's all I've done, right? I still need to subtract off what? That's f of x plus h. Minus what? F of x. Yeah, which is the function itself. So that'd be x cubed plus 2x minus 3. It's all over h. H is going to 0, but the top's also a 0 on direct sub, so I've got problems. What did I say would happen here if you did it right? Everything without an x will disappear. Let's go see if I'm lying. X cubed, will it disappear somewhere along the line? Down here, right? Because it'll be a minus x cubed. H in it, H in it, H in it. 2x, will it disappear somewhere along the line? Yes, right here with the minus 2x. Minus 3. Well, yeah, I'll have minus the minus 3. So there it goes. Everything without an h in it disappeared. Then the same thing will happen every time at this juncture. What's that thing? What am I going to do now? Factor an h out. Okay, so I'll have a limit. As h, my limits get messier and messier as not only the days go by, but the weeks and months go by. Writing limit gets, I write it all the time. Well, there's my limit. I'll factor an h out of the top. It'll be 3x squared plus 3xh plus h squared plus 2 all over h. What'll happen now? The h's cancel. Thank you. Gone. I eliminated my issue. We just had a whole chapter on limits, and I said once the issue has been eliminated, what do? Plug it back in. So every h up there is going to go to 0. That means you're going to go to 0, you're going to go to 0. What's staring you in the face? 3x squared plus 2. What did our shortcut give us? 3x squared plus 2. So my f prime, my derivative, will equal 3x squared plus 2. What does that tell me? What is it? Because that's important. Yeah, I went through all this arithmetic that I'm actually, after today, not going to do again unless I just choose to do the extra credit. But what is that? Slope of the tangent lines. Now, no matter what number you square, it's always going to be what? Positive. So my derivative is always positive. Could be 0, right? What would that tell me about the original function? If all the tangent lines have positive slopes, what's the function doing? Everywhere. Increasing. And it was a cubic, right? So my guess is, if I were to graph the original on my calculator, it probably look like that. Right? That should make sense. What's the slope everywhere along here? Positive, 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 positive. Might be 0. Maybe it depends on how long we flatline in there. So maybe a 0, but it actually won't ever be 0 because the 2 is the lowest it's going to go. So you get how that's working? So if I said, what's the derivative at 3? What would you do with the 3? Plug it in. It'd be 3 times 3 squared plus 2. It'd be 27 plus 2 would be 29. What does that mean about the function at 3? It is on a very steep shout out to infinity, right? Very, 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 very steep. Use your calculator to calculate the derivative at 1. You know what it's going to be. Plug it into your derivative function, and it's 3 times 1 squared plus 2, right? Go to your calculator. Remember when you go to your calculator, hit math 8, you enter the original function in it, not the derivative, or you'll be taking what we call a second derivative, and that's a whole nother story. This goes in for your function at x equals 1. Just make sure you can use your calculator. It should spit out a 5. Did it? Yes. Yeah, another thing is sometimes it'll be like 5.0001 or 4.9999. Your calculator does its best. So assume that it's due to both computer programming and the high level of math you're asking your calculator to do. It gets a little wacky at the end. But it is 5. All right, so one more. I know it's a lot of notes today. It is what it is. It's the first day. I think that page is over. Now, watch this one. Let's do this using what I call, now when I introduce the power rule in a few days, you're going to be going like, oh, we already know it. But that's okay. We don't have to go in the order of our book, right? So this function is really 5 halves x to the negative second. I think you'd agree with me that if I wrote it as a product like that, it'd be 5 halves times x to the negative 2. I told you that you could do the derivative by bringing the power out front. It'll cancel with the 2 on the bottom, leaving a negative 5. Are we okay with that? And then I said you drop the power 1. What happens when you drop negative 2? 1. Negative 3. So if I know my answer because Mrs. LaRue is sharing the power rule with me ahead because every year people do anyway, it'll probably come through the Zappas, filtered their way on through, and then he'd be tweeting out, snapping everybody, hey, you can do it this way, and then nobody would do it my way. So gotta do it this way once. Are you all right with that, Larkin? That will be my answer. Now I'll do it the long way. Just today. Here we go. How do I get the derivative? Today we're using the limit process or the definition of the derivative. It is a limit as what happens? Let's see if you got it down. Limit as h approaches 0. Thank you. Really what I'm doing visually is squeezing that secant line right on top of the tangent line. What do? I do y2 minus y1. You might say that's not what you're writing. It is. Over x2 minus x1, and it was x plus h was my second one, and my first one was x, so it's just h. So then it becomes the difference quotient. What is f of x plus h? I've got my limit. I've got my, there he is. Oh boy. All right, there we go. F of x plus h will be 5 over 2 times the input squared. You can kind of see why I did that difference quotient day so that this isn't foggy today. In the past, I haven't always done that. And then people are like, where'd she get the... Anyway, so my f of x plus h comes from putting x plus h in for x. And then I have minus f of x all over h. Right now, that's 0 over 0. You can prove it to yourself, but it is. That's a problem. I need to get h to cancel, so it's not there. In order to do that, I need to clean it up. Last chapter, what did we do when we had complex fractions that needed cleaning up, Allie? Crisscross applesauce. Let's go do that. We're just going to have to make some executive decisions along our way, but I think I'm just going to have at it. 10x squared minus 10 times x plus h squared. There's crisscross, right? All over, multiply across, 4x squared, x plus h, quantity squared. And it's all over h. What did I say to do in that scenario? Drop it. Yeah, it's actually times 1 over h. Remember, this is a limit. H is getting squeezed towards 0. Here's the deal. We're now concerned about the top because I want to get all non-h terms to cancel and factor an h out. So don't mess with the bottom, right? You want to cancel with the bottom, so there's no sense expanding the bottom out. You want it factored. But the top, you will want to clean that sucker up. So I have 10x squared minus 10 times. Go ahead and spit out the model, Brandon, for me, for x plus h quantity squared. What is that? Excellent. Thank you. All right, so there's my top expanded. Bottom, I'm just going to put it there. I'm not going to rewrite it again. You can if you want, or just leave it. I'm concerned right now with the top. On the top, do the non-x or the h terms cancel? And you have to picture going like this. There's your minus 10x squared minus 20xh minus 10h squared. Notice the 10x squared will disappear, right? So what's left would be the minus 20xh from this middle dump and the minus 10h squared from the last dump. The first dump causes that cancellation that I promised you. All right, this is a limit. Boom. And I'm all over that stuff. I'm not going to rewrite it. You don't need to. What did I say always happens here? I can take an h out, can I? Yep, I can, Riley, so we'll do that. So now I'm going to rewrite the whole thing, and then we are done. Limit. H approaches 0. I'm going to take an h out. I'd have, sorry. What am I going to have here? A minus 20x, then what? Minus 10h, right? All over. And I'll rewrite the bottom now. It was a 4x squared times x plus h quantity. I was just letting the bottom sit because it wasn't my problem. What happens here, Eli? H's cancel. Just eliminated my issue. Now that the h's cancel, Kev, what do I do? I don't need to. No point, really. After your issue cancels, what do? Plug it back in. You're going to put a 0, not in for x. You're going to put a 0 in for h, into what didn't cancel right there. And it's going to go right here. So I'm going to let you digest that because I'm going to do that without a rewrite. So on the top, h canceled. And I have a minus 20x minus 0. I have a minus 20x. On the bottom, I have a 4x squared that nothing happens to, and an x plus 0 squared. Why did I drop my limit? I'm replugging it in, right? I'm done. So when I reduce this, I end up with a negative 5 from these canceling. X over x to the 4th leaves an x to the 3rd down here. What did we get with the power rule? Identical. What, more importantly though, what is that? What does that tell me? Slopes of the tangent lines. Give me two other ways I can name it besides y prime. I call it f prime or dy dx. My favorite dy dx, but they don't introduce that in our book for a little bit. So what would be the slope of the tangent line at 1? -5 means the function's going downhill and going there fast, right, or steeply. Go do it on your calculator, and then that's it. So I want you to try that math 8. Original function goes in, hit x equals 1, and it should give you a -5. And while you're doing that for homework, nothing due tomorrow, but if you let it all sit till Wednesday night will be a big assignment. So you have enough in your brain to start this assignment. I wouldn't go to the second part. 1 through 23 odd I'd focus on if you're going to do any homework. What? Yes, yeah, but they're not all those. Like the first 7 aren't, they're reading graphs and stuff. So yeah, you will do them the long way. You don't know the power rule yet. You're not supposed to know it until 2-2, like till Thursday. So